everybody, I'm Brian, and today we are going to talk about classic data center networks, not the AI ones today, but that's going to be a 3-tier or a leaf spine network. So stick around and we'll get into it. Let's get into it. Okay, so yes, there is more than one way to make a classic sort of data center network. Again, we're not talking about the AI stuff here at the moment. Oh, hey, there's one way to make them too. Okay. But how do you pick? Well, what it comes down to is that if most of your traffic is going back and forth between like users and your servers, then you're probably going to use something like a 3-tier network, though it depends on when you built it and all too, of course. And if most of your traffic is going back and forth between your own equipment in that data center, then you're way more likely to pick a leaf spine topology. We're also going to have sort of a bonus combo there at the end. It'll be something to do with a super spine. Yeah, we'll get to that. All right, but hey, if we're going to be talking about these different network diagrams, I think we're going to draw it. So, Tiny Brian! Yeah, push the button now. Tiny Brian! Okay. So here's the deal. Let's start with that 3-tier topology. And this is the sort of classically what you would do with a core and distribution and access. Except in the data center, you're much more likely to call them, instead of an access, call it a top of rack or TOR. And instead of a distribution, you're much more likely to call it an end of row, or you might see it as EOR. And yeah, we run out of creativity and we just call the core a core, almost certainly. Okay. So what does that look like? Because, I'm tiny, we're drawn. Well, each of your racks of equipment, very likely up at the top, has some switch. And then you've got a bunch of servers or storage or whatever else in there. And next week, I think I'm actually going to go into a little more depth of what that hardware in a classic data center would look like. But again, this week we're just focusing on the network itself. And so yeah, that switch up in the top of that rack of equipment, again, we very conveniently call top of rack. Each of those top of rack switches has a whole bunch of cables running down to all of the machines in there. And that's going to be just fine for all of the servers in that rack of equipment to talk to each other, or storage or whatever else is in there. They can just do it through that switch almost certainly. But you're going to have more than one of these things. In fact, you're likely to have a whole row of them. And you want these different racks of equipment to be able to talk to each other too. Or for that matter, again, we're focused here mostly on getting traffic from our users to these, and your users probably not in the data center. So we're going to have some way for them to, talk to each other, but even more importantly here, get out to the wider world. And so one of these racks of equipment almost certainly is going to have an extra switch in it that's going to be our end of row. And all of our different top of racks are going to be wired up to that. Okay, great. Now we've got some path between all these racks of equipment. And yeah, these are going to be almost certainly faster links than whatever is connecting up those servers, right? So 10 years ago, 15 years ago, it would have been probably 10 gig going down to these servers and 40 gig going up to that end of row. Today, man, it really depends, right? Maybe, just it really depends on your scale, but might be like 100 gig to that end of row and 25 gig to those servers. Okay, and that's great. Now we've got this whole row of equipment that can talk to each other. But again, we're trying to get out to the users. So, I'm going to need a cheat here. Through the cunning use of more copies of Paint and copy and paste. Let's see, what we're going to do is we're going to take our row and shrink it down. And let's get a couple of more rows. Paste, right? And this data center is full of all these different rows. Well, great. Each of those end of row switches now would also be connected up to some core. Yeah. And again, You'd want this to be, if possible, even faster than your connection back to that end of row, but it just depends, right? Like, what you can get here. Again, honestly, it's probably similar speed. So maybe this is today 100 gigs still, or a bunch of years ago might have been like 40 gig for these faster links. Okay, but it just really depends on what kind of bandwidth you're dealing with here. Even better if it's more than one link and like an LACP port channel or something. But okay. Now, there's a way for all the servers in here to be able to talk to each other. But again, really, we're trying to get out to the users. And so that core almost certainly would have been your router. You might have been routing at the end of row or even the top of rack as well. But a bunch of years ago, the core would have been where you're routing. Say in the last 5 years, yeah, you're probably routing at least at the end of row or maybe top of rack, and all these links are routed. But either way, the core is your main way in and out of the data center. There's going to be some almost certainly firewall the other side of it. Yeah, the little castle thing's not like the official, but it makes me happy to draw it that way. And then the other side of that firewall is going to be like the rest of your corporate network or the internet or some of both, right? And all of your users, right, you, me, whatever else, are out there in the world on our laptops, our desktops, whatever. And there's some mysterious amount of network between here and there. Firewall's there so that only the traffic that you want gets in and out of that data center. And once it's, you actually go to some IP of some particular machine, right, the core presumably would route it to the right end of row, that's going to route it to the right top of rack, that's going to get it to the right server. Okay, great. And this is our 3-tier architecture, classically core, distribution, and access, or in the data center, more likely core, end of row, top of rack, just different ways of saying the same thing. Awesome, and this is great. Nothing particularly wrong with this, except, well, if you don't have most of your traffic going in and out of the data center, if it's mostly going between these different devices, well, we'd probably want that other topology we were talking about, that leaf spine. Leaf spine, yeah, well, and here's the other bit of it. I actually drew things a little sideways, hang on. Let's see if I can cheat. Haha, cheating engaged. so usually in diagrams, you'll draw it basically so that, like, your internet or whatever, your core is like above your distribution or whatever. Anyway. So this traffic here in our 3-tier with our top of rack, end of row, and core, most of the traffic anyway is going back and forth between these users and our servers, like we said. And this is very often called north-south traffic. And that's literally just because it's that traffic going up and down in our network diagram like this. And so, yeah, this is for our 3-tier architecture. If instead we had mostly east-west traffic, you might hear it, which is to say most of our data, our bandwidth, our traffic is going to be between the equipment in this room. That's when we're going to be looking for sure at that leaf spine topology. So let's go draw one of them. Alrighty, we got our row of equipment again, and we're starting the same way. Bunch of servers in this rack of equipment, top of rack on each of those, except, well, we're not gonna call it a top of rack this time. So, like, you can call it whatever makes you happy, but for this topology, it's gonna be a leaf. All right, so leaf 1, 2, 3, 4, instead of top rack 1, 2, 3, 4. And we're still just, each of these leaves is connected up to all of the servers in that rack of equipment, and we're still going to have some other switch that we connect up to, but now we're going to have more than one of them. Minimum of 2 of these, and we're going to call them a spine. So there's our spine 1 and spine 2. Cool. Now, this is still going to be in some of these racks of equipment. I'm just drawing them above here for clarity. And then here's the rule. Every leaf is connected to every spine. And so here's what I'm going to do. I'm going to draw these as 2 different colors to try and make it a little bit less of a jumble in here, a little more legible. But like these are representing all the same type of whatever cable. And again, it's going to be whatever like we have available on these these top of racks. That's the faster port there, right? Is it 10 gig? Is it 100 gig? Is it 1600 gig? Whatever the fast port is on these leafs, that's what we're working with. Okay, so drawing all of my connections from leaf 1, 2, 3, 4 up to spine 1 as purple, and let's just make all of our connections over to spine 2 as green, just to hopefully make this a little bit less of a jumble. Okay, now every leaf is connected to every spine. Again, at minimum 2. You can have a lot more than 2, but 2 is the minimum and a pretty common choice because money. And very, very, very likely every one of these cables we're talking about here that's a 100 gig link or whatever it is going to be a routed link. So every one of those is a teeny tiny little network, probably like a /30 if it's IPv4, or /31 even, with either way 2 usable addresses on each of these. And we're not going to worry too much about that. But yeah. And now, if any server in any of these racks want to talk to any server in any other rack, it's one hop away. And it's a redundant, load balanced hop. Yeah, okay. So we've got to put some like names on here so we can talk about somebody. Let's say this is server 10 over here in the bottom of our rack 1 there with leaf 1. And then it's server 40 over here in the bottom of our rack number 4 with leaf 4 over there. Well, if they want to talk to each other, they're going to have some IP. Probably there's actually some VM running on there, but whatever. They're going to have some IP. Say this one is 10.0.10.100, and its default gateway is 10.0.10.1. And over here, it's 10.0.40.100, and 10.0.41 is its default gateway. All right, well, 10.1, that default gateway is going to be on this leaf 1. And when this server 10 wants to send traffic from 10.0.10.100 to 10.0.40.100, it's going to send that traffic. There we go. It's going to send that traffic from its IP 10.0.10.100 over to 40.100. That's going to go up the wire, hit its default gateway there on leaf 1, that 10.0.10.1. It's going to look up its routing table and say, how do I get to 40.100? And it's going to have 2 possible next hops. One's going to be spine 1, the other's going to be spine 2, and flip a coin. It's going to pick one of the 2 of them based on its hashing algorithm, blah, 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 right? And so let's say it goes through spine 1. Great, well, it goes up to spine 1. Spine 1 checks its routing table. How do I get to 40.100? Oh, that's available out this interface. And the packet goes down the wire over here to leaf 4, which checks its routing table and says, oh yeah, it's on my VLAN, whatever. Routes down to there and sends it off to that computer. Server 40 gets it. Yay! When the response comes back from 40.100 back to 10.100, swap these. There we go. Something like that. Well, cool. That's going to go. This server 40 says it's from 40.100 off to 10.100 for the response. It's going to send it to its default gateway of 40.1, goes up the wire, hits its default gateway. Leaf 4 checks its routing table, says, how do I get to, there we go, to 10.100, and flip a coin. Might go to spine 1 or spine 2, hashing algorithm, blah, blah, blah. Let's just assume it takes the other path, spine 2. Great. Spine 2 checks its routing table. How do I get to a 10.100? Oh, that's out this link over here. Sends it out to leaf 1. Leaf 1 gets it, checks its routing table, sends it down to that server. Huzzah! Yeah, and in this way, we're sending traffic about half the time between these 2 racks, leaf 1 and leaf 4, about half the time through spine 1 and about half the time through spine 2. We now have additional bandwidth, right? We've doubled our bandwidth here, and we're sending about half that traffic through one switch and about half through the other. So that's going to allow for this, again, additional bandwidth, splitting it up through those 2 sets of 2 ASICs on those 2 different switches. Yeah, right? And so now we're load balanced across this extra bandwidth between the 2 of them. We're also now redundant. If one of those spines fails, or I powered it down for a firmware update or whatever, blah. Well, gee, I guess now when these servers are sitting back and forth to each other, they'll check their routing table, and their only option is going to be that next hop through spine 1. Sweet, so it's just going to set it all through there, and I'm reduced bandwidth now during this time that I'm updating that thing, but it didn't all shut down, right? Bring it back up. Woo. And then I could go do the update on spine 1, and well, yeah, now everybody's going to send their traffic through spine 2 without having to bring everything down. Oh, sweet. Okay. And now most of this traffic, right, we're building this up for additional bandwidth between these different racks of equipment. We also have consistency, right, our redundancy, our load balancing, and consistency, because like I said, all of these servers in these different racks of equipment are equally far from each other in this row, right, because it's all one hop away. Right? Well, 2 kind of, but it's just through spine 1 or spine 2, right? And it's just as far if server 10 wants to send something to server 40 over there as if it wants to send it to server 20 or whatever I call that thing in the bottom of rack 2. Yeah, up 1, down 1. That's all. And so this is a leaf spine topology where every leaf is connected to every spine. And we have redundant, load balanced. Also, I throw in non-blocking, but that's getting into a whole spanning tree thing, routing. We're happy. Links between things. And this thing I've described here where I'm routing on all those links, this would be a layer 3 leaf spine topology because we're routing. Huzzah! Okay, and so this is a bit more common today, especially if you got a whole bunch of virtual machines where you're migrating them around and you want to make sure you got plenty of bandwidth in there, or if you got like users and machines and whatnot that are accessing applications that are in here, but like they're just pulling up a web browser that points to the management interface, but meantime there's actually big databases worth of information that are being manipulated, moving big chunks of data around inside the data center. Okay, leaf spine topology is still pretty ideal. Okay, but before, I'll go back over. Yeah, we could move stuff around through that that row of equipment through our end of row. We basically got a second end of row and design things a little bit differently for our leaf spine. But we still got to be able to talk between all of our different rows of equipment. For that matter, get out to the outside world. So our one row isn't going to be enough. Well, let's hang on a second. Open more paint and expand. Okay, we're just gonna shrink things down a little bit and let's get a couple of rows in here. Okay, arrange things a little bit differently this time so we can still see some details. Now there's two basic different ways to be able to have these different rows communicate with each other. The classic, if leaf spine can be classic, way of doing leaf spine would be that the spines only connect to leaves. Don't do anything else with them, they're just interconnect for those different leaves. And so the sort of classic leaf spine way that you would do this, and depending on your vendor and the topology they're suggesting, the VAR, value-added reseller, that you're contracting with to help you set all this up, they might have opinions about one way to do it or another. But the classic way would be to have an extra leaf in every row. And this extra leaf would be called a border leaf. So one in every row. And let's just connect those up to our spines in each row. Excellent. And now this border leaf is just another leaf, but now it's also your way of getting in and out of that network. And what do you do with them? Well, you'd still probably have a core. Doesn't exactly fit into our leaf spine idea, but yeah, you'd still have some core. Every one of those leaves is hooked up to your core. You're going to have some firewall. And then, out to internet and, or the wider network or whatever, right? And so this would be the classic leaf spine topology, again, where you're focused primarily on lots of bandwidth between all of those devices in that leaf spine topology, sometimes even referred to as a fabric. And then you got lots of traffic between there. Now, there's some limitations here with this idea of a border leaf. First off, we might want more bandwidth up to the core. And we could have, again, multiple links with port channels, right, for additional bandwidth that way. But this whole leaf spine thing here too, where theoretically we just have our two layers of leaf and spine, well, I mean, yeah, but if you put the core above it instead of next to it, oh look, I kind of got 3-tier and I still had my core anyway. So there's another way to do things too. Instead of this whole border leaf thing, we could say that we've got leaf spine and super spine. Just fix this. What do you say? Super spine. Yeah, super spine 1, super spine 2. I love it. Okay, and now, just like every leaf was connected to every spine, now every spine is going to be connected to every super spine with redundant, non-blocking, active, right, like great redundant links. And yeah, the mess. sorry. Even with keeping the colors separate here, this gets a little crazy. But yeah, now every spine is connected to every super spine with our redundant, non-blocking, load balance links. Huzzah! And so we've effectively reinvented our 3-tier with our leaf spine and super spine, which we may as well call top of rack, end of row, and core. Again, the key difference is our redundant links everywhere with that minimum of 2 spines, 2 super spines. You can definitely have more. It's just you kind of run into limitations of how many of those fast ports do you want and how much budget do you have for all these things, because even ignoring the price of those switches, every transceiver and cable is pretty pricey. But this is our leaf spine and even super spine environment. And that super spine thing, instead of the border leaf, that is that sort of extra kind of in-between option. And again, why would you pick this versus the border leaf? First and foremost, if the solution you have purchased from your vendor says you are going to use border leaf, yeah, right, that's what you got. Right? Especially if there's some kind of automation involved, it's going to have a cookie cutter. Here's what your network looks like. You just got to do it. But if either it's not defined in that that topology that you've essentially purchased as a package kind of thing, or if you're just trying to put your own thing together, this might be the better option because it sort of balances the two of them, where now I can still have plenty of bandwidth north-south, right, with my super spine going straight up there, and also our east-west, plenty of bandwidth between as well, so that we're minimizing the number of hops between any given server in here, and we've got a great deal of bandwidth redundancy and all that between all the stuff in this room, this data center, and the rest of the world. Okay, so this was our look at a modern non-AI data center network. Again, that was the classic 3-tier if you don't need a ton of east-west traffic or traffic between your different equipment, and that leaf spine or maybe even super spine if you do need a lot more bandwidth and redundancy. Alrighty, let's see now. Next time, we are going to be jumping into a look at the hardware in a classic, but still current non-AI data center. And what we're building towards is, yes, letting you understand what's out there and what you might be interacting with to better understand it, but also to be able to compare and contrast that with a modern AI data center, where we'll get into the networks and hardware you see over there as well in the next few episodes. Y'all, I am still having a blast, and I hope you are too. If you know somebody out there that might enjoy this, do me a favor and send it their way. And if you got something on your mind, let me know down in the comments. You rock. See you next time. I'm making the noise, la la la. Blah, 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 blah. All right.